I'm David, and I'm the coordinator of the Maths Learning Centre, and today's Maths Learning Centre seminar is about understanding maths notation. And I'll let you know how it's going to run in a moment when I get up to that bit. But it's not necessarily going to take the whole of the 50 minutes, so hopefully you'll be able to get to wherever you want to go after that. So, oops, you can skip that bit. So, the transition team has asked me to get you to put your details down. There is a sheet coming around, so if you don't get it by the end of the seminar, come down and write your name on the sheet. And whoever has it at the end of the seminar, please bring it down and give it to me. Thank you. Okay, so these are some places where you'll see maths notation. So obviously you think that you will see maths notation somewhere in your degree. So here are some places. In a maths course, statistics, physics, chemistry, economics, psychology, and almost any discipline at all, there will be some notation, maths notation there, mainly because if you're at a research-intensive university, you're going to have to do statistics at some point. So that's the way of things. So you know why you want to use it, but this is why people use maths notation. I'm going to tell you this because it's not just because people are bloody-minded and want to make things confusing. People use maths notation because it makes life easier, and it makes life easier for the following reasons. It makes it easier to write maths down. Okay? If you had to write all of the maths that you needed to do in words, as they did before they invented the maths notation, it would be damn hard. So that's one of the reasons that maths notation makes life easier. It's easier to be accurate. English words, or words in any language, mean different things in different contexts. Maths notation always means, well, almost always means the same thing in certain contexts. Sometimes English words mean multiple things even in the same context, but maths notation always means the same thing in a particular context. So it's easier to be accurate about things if you've got maths notation to do it with. It's easier to communicate with other languages. That's the main reason why most of our maths notations were invented. In the days when people did mathematics fully in words, if you wrote your mathematics in French, someone in England couldn't understand what you meant. And now that we have maths notation, I can read a mathematics paper in geometry, which is my area of mathematics, that's written in French and understand the gist of it because it's mostly written in mathematical notation. And finally, it makes it easier to think. If you can turn your problem into notation and you have rules for using the notation, you can think on paper. So if you write your maths on paper in notation that makes it easy to write on paper, then you don't have to keep it all in your head while you're thinking about it. You can put it on the paper to help you think. So the purpose of having maths notation is to make it easier to think about maths and to communicate maths. So don't feel, it's important to learn, because the point is that once you've got an understanding of it, life will be easier than it was without it. And this is my advice on how to understand maths notation. So these are the questions you should ask if you're faced with a new mathematical notation that you've never seen before, or one that you're trying to learn more about. So the first thing you need to ask yourself is, how do I say it? There's nothing more embarrassing than going up to your lecturer and pointing at something and saying, "What is this squiggle? I do not know what it is." If you at least have a name for it, then you can ask questions about it. If you have a name for it, then you can search for it on the internet. But if you have some random squiggle, you can't search for it in Google because you don't know what it's called. So how do you say it is the first step to understanding it. The next question is, what does it mean? And what does it mean doesn't necessarily just mean what does the maths mean. It means how is it related to everything else, which we're going to get to in a second. So how do you say it is not the whole amount of what does it mean. You're saying, in this context, what are we using it for? What is it trying to say? How is it going to be figured out? Those sorts of things. And I'll get to that as an example in a second. Next, you want to know what the rules are for working with it. A mathematical notation is written on paper, and it should be possible to do stuff to it, like use it in a formula. And there will be rules for what you are and are not allowed to do with it. There will be things that you're allowed to put next to it. There'll be ways for multiplying things. There'll be ways for adding things. Those sorts of ideas. And you want to know what the rules are. And what are the rules for even how to write it down? Sometimes, some maths notations, if you write it in a certain way, it doesn't mean anything at all. And sometimes if you write it in a different way, it means something different. So you need to work out what the rules are for writing it down and for connecting it with other stuff. And finally, how is it connected to other ideas? So when you say, what does it mean? You should ask this question as well, because meaning is usually about connection. So if it's connected to another idea, it might be a similar notation to some other notation, and it might be similar in terms of the rules that you're allowed to use it. Or it might be look the same as some other notation, but be different in this context, so you should know how it's connected there. Or it might be that it's used in certain places, so it might be that this maths notation is only ever used in chemistry, and it's good to know that it's used in chemistry and it's used in these types of places, and they're the only places that you'll see it. That's what I mean by how is it connected. Okay, and you could also just connect it to random other stuff that you happen to know. Movies, colours, shapes. Because the sensation of understanding in your brain is to do with how your ideas are connected to each other. The more things a new idea is connected to in your brain, the more you will feel that you understand it. So connect it to other stuff and you'll feel like you understand. So as an example, this mathematical notation, we say it as the square root. So with a 25 underneath it, it would be the square root of 25, and some people just say it as root 25. Hopefully you've seen this symbol before, but if not, don't be embarrassed. What does it mean? Well, the square root of the number x is the number that you would square to get x, so root 25 is 5, because 25 is 5 squared. That's what it means. It's the opposite of squaring. Okay? All of this will be on the website afterwards. So what are the rules for working with it? And this is what I mean by what are the rules. So I'm illustrating what I mean by that. So you can distribute it over multiplication and division. So in particular, if you've got a times underneath it, then you can just do the times after. You can separate that and do the roots separately and then times. If you've got a fraction underneath it, you can do the roots on the top and bottom separately and divide. So that's one of the rules for how to deal with it. But there are things that you are allowed to do, and there's also things that you aren't allowed to do. You can't distribute it over addition and subtraction. So if you've got a plus underneath it, you can't do the roots separately and then do the plus afterwards. That is totally not true and completely and utterly wrong. Okay, so you can't do that. So it's good to know that. And if you want to have a number, if you've got a number outside your root and you want to bring it inside, you'll have to square it along the way. So the 3 comes inside and it will become a 9 because 3 squared is 9. So this is what I mean when I'm saying what are the rules for working with it. Figure out how it interacts with other stuff. It's a square root, it's designed for dealing with numbers. Well, how does it behave when it's near other stuff that we do with numbers, with times and divide and plus? Okay? That's the sort of thing that you want to ask yourself when you learn a new maths notation. How is it connected to other ideas? Well, firstly, it was the opposite of squaring. And secondly, you can write it in yet another maths notation. So root x can also be written as x to the power of a half. And they mean the same thing, but they're different notations. So that's what I mean by connecting to other things. We're saying that's connections to what it means and to other notations that mean the same stuff. These are the places that you'll use it. You might use it to find distances, say when you're doing physics and you're finding the length of a vector. You might use it to find the standard deviation if you're doing statistics. You might use it to solve quadratic equations. So they're the places that you'll be seeing that notation. Warning yourself that that's where you'll use it for, so that you can make sure that when you see standard deviation, square root will pop into your head. And thirdly, we can connect it to other notations that are similar but mean something different. So the cubed root and the fourth root and the fifth root, they all have the same sorts of rules for how they behave near times and divide and plus and minus. So if you can make those sorts of lists for yourself and maybe keep them somewhere useful, so that when your lecturer suddenly does something, you're going, oh, that looks like it's a new rule for how to use square root. I haven't seen that one before. I'll add it to my list. Okay? That's what I'm trying to get at here. Now, I wasn't really trying to teach you about square root, but if you want to know more, please ask later on. But I wanted to show you the sorts of things that I'm trying to get at when you want to understand a maths notation for yourself. Because at some point, there will come a point in the future when maybe you're in third year or you're doing a postgraduate degree and there won't be a Maths Learning Centre at your new university and you won't be able to talk to them. You're going to have to figure it out for yourself at some point, and this is the advice that I want to give you. All right. So I've told you the questions you should ask yourself in order to understand a maths notation, and I've told you where maths notation is going to happen, and so now it's time to find where the answers are. So cool, you might not know all those answers about square roots. This is where to find them. So the first one is to listen to the people who are teaching you as they write. Okay? So that's the best way to find out what the name of something is. Because most lecturers, if they're good, will say aloud what they're writing. So if you have a squiggle that you don't know what it is, watch, and the next time they write it, hear what it's called. They will also say certain things about what's going on in their head when they figure out something as an example. So they might be writing here on the document camera, and they will be using a square root, and they'll say, I have to square it when I bring that number inside. They may or may not do that. Okay, but if they do, you should be listening for it, because then you can find those rules. The next thing to look for is definitions in the notes or the textbook. So suppose you're looking in a textbook, and this happens a lot in economics, and they suddenly use some sort of maths notation that you don't know what it means. It's usually somewhere nearby in the textbook. If you just go back a few pages, you can usually find what that notation stands for somewhere nearby. Okay? Or there might be a footnote which says it's in the Appendix A. So if you find notation that you're unfamiliar with somewhere in a book, then look around it in the pages nearby, and there should be a definition somewhere. Okay? And thirdly, when you see a written example, because there will be plenty, in a textbook there's lots of examples, and you've got your lecture notes and all of these other things, notice when they do things, and notice other times when they don't do stuff that you thought might be possible. Okay? You're going to have to try and figure out some of the rules for what's allowed and what's not allowed, and those written examples are the places to see them. So when they do something, they do some algebra, they've got their square root and they split it apart over the times sign, you'll notice, well, that must be okay. My lecturer did it, it must be okay to do that, I can do that. So that's the sort of thing you want to look for. It's harder to find things you're not allowed to do because lecturers won't do them because you're not allowed to do them. But so don't assume that if you can do it for times, you can do it for plus as well. It's almost never true that you can do things for both times and plus. But if they do it for both, then it's a really rare situation that you can, and so you should write that down. And finally, you should ask someone, because if you've tried your best, then there's only so far you can go with the information you've given, and sometimes you just have to ask someone, what is that squiggle? So, for example, the Maths Learning Centre on Level 3 East of Hub Central, open 10 a.m. to 4 p.m. on weekdays. So and I'll be there. You see I'm still wearing my Maths Learning Centre name tag. Anyone wearing one of these you can talk to and ask about anything, including maths notation. So here in the Flenchy, if you go out the back door and turn right, there is a back door to Hub Central just there, and you can actually get into the Maths Learning Centre from right there. But if you do get lost, just ask the very friendly Hub Central information team and they'll bring you right to us. We think that notation is really important, and we think that the embarrassment of not knowing what something is called is an unnecessary embarrassment. No one should be made to feel that way, which is why we have the Greek alphabet on our wall, which I'll get to in a minute. And it's why we have the families of number on our wall, and it's why we're extremely friendly so that you can ask us anything. So if you do get to the point where you're going, look, I just can't figure it out, come and ask, and we'll talk about it. Okay, so the next part of the seminar is I'm going to talk about various different types of notation. So I've given you all the advice I can, really, about how to understand a new notation. If you do come to us and say, I've got this new notation, can you help me understand it? I'll help you go through those questions and find the answers to them. And really, for each of you, it'll be different depending on what courses you're doing and what degree you're doing. So the rest of the learning about notation is extremely personal. What I'm going to do now is go through as many maths notations as I can think of, hoping that at least one of them is one that you will see. Okay? And if some of them look too crazy for you and you don't think you'll ever use them, ignore it for now and come back later and look them up. And some of it's really just note, David knows what this is, so I can go and ask him at some point, okay? So that's what I'm going to do now. And I've split them into 4 categories. Notation for naming things, notation for making statements about things, notation for creating new things from old things, and notation for abbreviating words and phrases. They are the 4 main purposes of mathematical notation. And if you can know which category it belongs in, it makes it a little easier to understand. Okay, and that's why I'm going to go through this way. At the end, when I've finished, there will be about 15 minutes left, and I'm going to ask you if you want to know anything else or any other mathematical notation, and I will write it on paper if it's not already in the PowerPoint slides, and that paper will go on my website as well. So, notation for naming. So often in maths you need to name something that you're talking about. A classic example is let x be the number we want to find. So what we've done is we've used the letter x to give a name to the number that we want to find. Okay? So if your notation is simply just giving a name to something that doesn't currently have a name, that's what it's for. It's so that you can make it easier to talk about it. Since you've called it x, you can now say, well, x plus 1 is equal to whatever it is, or x squared minus 3x. So once it's got a name, you can start writing maths about it. But until it had a name, you would have had to just call it the number, as they did in ancient Egypt, and they called it the heap. Okay, and they would have to write it all in words. So now that we've got maths notation, we can cut down on some of those words so that it's easier to understand what we're doing. And these are the different types of naming things that I'm going to go through. I'm going to talk about the Greek letters, some well-known objects that have names of their own, vectors, subscripts, and distributions. So I haven't mentioned there the English letters. It's always okay to give something a name like X or A or F. But apparently the English letters are not enough. We've got 26 and 52 if you count the capitals and smalls as separate, and we need the Greek letters as well. This is the Greek alphabet, the ancient Greek alphabet, and these are the English names for those letters. Okay? They're pronounced slightly differently in actual modern Greek, and probably differently in ancient Greek as well, but this is what they are called. This is on our wall in the Maths Learning Centre, if you ever want to just sidle up to it and have a quick look when you're not sure. And I'm going to read them aloud to you because everyone says them differently. So that first letter is alpha. This is, I call it beta, but some lecturers will call it beta, and some lecturers will call it beta. Okay? This is gamma, delta, epsilon, zeta, and again it could be zeta or zeta, eta, same rules, theta, it could be theta or theta as well, iota, some people will call it iota, okay, kappa, lambda, mu, though some people will just call it mu, so, which is what it would be in actual Greek, so mu, and the same with nu, which is called nu. This is xi, okay, because the x makes a x sound. Some people will call it xi, or possibly even z, or possibly even xi, but I call it xi. Lecturers are extremely proud of themselves when they can write the small xi, because it's difficult to write. It's got 3s, 12s in it, and it's hard to write. And you'll see them do it, because they're proud of themselves for having learned to write that letter. Omicron, or omicron, pi. Now, in actual Greek, they call this p, but we can't call it p, so we call it pi, because we've already got p. Rho, sigma, tau, some people call it tor, upsilon, some people call it upsilon, phi, some people call it phi, psi, chi. I believe in actual Greek it's chi, but some people will call it ki. Please never call it chai. That's wrong. It's chi. Okay, because that x is the x that's in the end of the Scottish word loch. So it's chi, not chi. And this is omega or omega, any one of those. So if you've ever heard people pronounce them, they're all the options. Really, no one cares. As long as you use the same thing all the time, no one will mind. But lecturers will call them differently depending on where they were brought up or what language they learned Greek letters in. Yeah, so there you go. I should have done that. See, I read them one at a time and I forgot that I had done that. So I should point out that these ones that I've coloured in red are the same as the English letters. Okay, so you will never see a capital A and expect to be calling it alpha, because it's just an A. So for the purposes of maths, this is the Greek alphabet, because Omicron is just O, for example, and a capital tau is just T. So that's the Greek alphabet as used in mathematics. Some mathematicians also use the Hebrew alphabet, which is even more interesting. So, okay. Now there are some well-known things that are always given the same name. So usually if you're doing maths, you can call something A, or you can call it X, or you can call it Y if you really want to. But these things always have the same name. Now the letter E can sometimes just be a random number, but in most contexts, the letter E is the number that's approximately 2.71828. It's the natural exponent, it's called. And it's used for exponential growth in things like chemistry and economics. The letter pi is representing the number pi, which is approximately 3.14159, which is used in circles, finding the areas of circles, and also in a whole lot of other strange and interesting places that you wouldn't expect it to be. This symbol means infinity. In a different context, it might mean a slightly different version of infinity depending on what you're doing. This symbol is the empty set. It's an O with a cross through it. It might also be written as a 0 with a cross through it. Now, you may never see that, but I need to say that that's what it is. So that means that if I say, what is the set of all unicorns with daisies growing out their nostrils, that would be the empty set, because there aren't any such things. Now, these are the families of number. On the Maths Learning Centre wall, there is a poster for each of them, and you might see them written in various ways. So if you're doing anything that's mathematical, they may use these symbols. So it's either, in a textbook, it's often written in bold, but on paper it's usually written as the letter with an extra stroke. Okay? And written in handwriting, it's slightly different again to what's drawn here. If you have a look at what's on the Maths Learning Centre wall, you'll see what it looks like. But we have n, which is the set of natural numbers, which begins at 1 and goes 1, 2, 3, 4, 5, 6, 7, and so on. Though I should warn you that some computer scientists think that it starts at 0. So just be aware. Z is a set of integers, so that's 1, 2, 3, 4, etc. And 0 and -1, -2, -3, -4. Q is a set of rational numbers, so everything that can be written as a fraction using whole numbers on the top and bottom, including the negative ones. So -1/2 is Q. That Q stands for quotient, which is another word for division. Rational comes from the word ratio. It doesn't mean numbers that make sense, it means numbers that are ratios. R is the real numbers, which is a set of all things that can be written with a decimal expansion, and that includes all the fractions, right? Because I can write 1/2 as 0.5. Okay? And real numbers are used to represent distances, really, and time and that sort of thing. They're lengths of some sort. And C is the set of complex numbers, which are the real numbers added on the square root of -1. And I really should have put the number I on there, actually. That's an omission. Okay, so if you ever see them in your maths course or elsewhere, that's what they're referring to. And I'm going to come back to using them in a different context again. But that's what those numbers mean. Those letters stand for, in most places, if you see them written in that way, then that's what they mean. Okay, so there are well-known objects. Yep. No, there's no symbol for the set of irrational numbers. I would say that normally, some people will write it like this, but that looks like the Roman 2, right? So that's a bit weird. You can say it's the real numbers without the rational numbers, but I'll get to that in a second. Okay. We're going to talk about naming vectors. So in physics and in maths, there are vectors. So vectors are normally arrows, right? Or they could be things with coordinates. So say a point in 3D would be something like, an X, Y, and a Z coordinate, and that will be a vector as well. And in most books, the vectors are written in bold. Okay, so the letter U in bold represents the vector U as opposed to a number like 3. Okay, but in handwriting, you'll have an extra mark on it. And they're all the things I've seen people use to mark a vector. I personally use this one, I underline it, to say that something is a vector as opposed to a number, but various lecturers and teachers will use any of those and possibly other things as well to tell you that that symbol is standing for a vector as opposed to a number. But I would say please, please, please mark your vectors if you're writing for a mathematician. It's good to say A underline V plus B underline U, but it is bad to say AV plus BU because it's difficult to tell which of these are vectors and which of them are numbers. So please mark your vectors because it really annoys people if you don't. And annoyed markers are less generous, right? So please do that if you have to write vectors. That's good, that's bad. So, subscripts. The name for a little number or a little letter down at the bottom of something is called a subscript. If it's at the top, it's called a superscript. But subscripts are used to give names to things. So you give names to things that are related in some way, usually. So that's how you do it. And you don't normally read the word subscript when you say it aloud. If I read this aloud, it would just be C1, C2, C3, C4, C5. If you wanted to tell someone that it was a subscript, you could say C sub 1 if you wanted. But if you say that aloud to a mathematician, they will automatically assume that it's subscripts. And all it means is that you've got 5 numbers and you've decided to call them all C. But they can't all be C because C represents one thing. So you've got the first C and the second C and the third C and the fourth C and the fifth C. You've just given them all a name and you've decided to call them all C. It may be that you want to have your vector and it's got 3 coordinates and you call the first coordinate V1 and the second coordinate V2 and the third coordinate V3. Okay, so usually they're related in some way when you do subscripts on them. They come in some order. Here's another one. This would be a polynomial. And normally it would have numbers in the place of those A's, but because they all belong to the same polynomial, I've given them names, A0, A1, A2, A3, and A4. And it is possible to not use numbers. You could use ER and EN. This comes in the engineering course called Engineering Mechanics Dynamics, and those E's represent vectors, and one is in the radial direction and one's in the normal direction. Okay? So, and you'll even see it, if you've studied statics, you'll see it already, and they'll say F sub AC, so they'll put a letters at the bottom to say what it refers to. So that you don't have to use a new letter, you can still call it F if it's a force, you just put a letter at the bottom to tell you which one it is. Now, people use the letter I, or possibly J, or possibly K, to refer to all of them in one go. So instead of saying C1, C2, C3, C4, C5, I could say CI, where I is 1, 2, 3, 4, or 5. It's just saying that, you know, I have a subscript, there is something down here, and the options for what to put there are 1, 2, 3, 4, or 5. Okay, so when a lecturer just says CI without any other qualification, it means that there's numbers that go in that spot to tell you which C that you have. That's all they mean when they say that. So those two statements there, the C1 up to C5 and the CI, mean the same thing, okay? And it's much more useful for them to put like dots in the middle here. Because if you had 100 of them, that's when it starts to be useful. You know, CI for I equals 1 to 100. Okay, so these subscripts are really used to just give names to things that you have decided what they should be called. The previous page was stuff, someone else decided that that number should be called pi, and pi is what it is called. You can't call it x because it's pi, right? So this is things that you've given a name to because you want to remind yourself that they're all related. These things are in statistics, and these have names of their own already. You can't decide what to call them. So if you've ever been in a statistics course, or you will be one soon, this is going to come later, and you can come back to this part of the seminar and see what I'm talking about. But a distribution is a description of how likely everything is. Okay, so you've got some numbers, and they come out randomly, and you want to know what all the options are and how likely every option is. And that whole description of how likely all the possibilities are can be all encapsulated in a single name that tells you everything you need to know about that. And the letter part tells you which family it comes from, and the numbers tell you more about which one within the family you have. So if this doesn't make any sense, let it wash over you and you can come back later. But N, 28.3, means the normal distribution with mean 28 and standard deviation 3. I should warn you that some lecturers put 3 squared in that spot. Yeah. So in the School of Maths, they'll generally put the standard deviation in that spot, but in economics and in engineering, they will often put the variance in that spot, which would be 3 squared. So watch out for whatever they're using, and that's just different people using different things in different contexts. T with a 14 is a T distribution with 14 degrees of freedom. You may also see that 14 written in brackets. Chi-squared, so that's got a superscript, that's squared, and a subscript, which is the 5. So chi-squared distribution with 5 degrees of freedom. This is the F distribution with 2 numerator and 30 denominator degrees of freedom. And this is the binomial distribution with 10 trials and probability of success 0.7. All I'm trying to point out there is that when you see distributions written down, the symbols that are there are just telling you which one to look for. So if you were going to look them up in a formula or in a table in a book, it will tell you where to go to look for them. Okay? And it's a name that describes all of the information about how likely all the possibilities are. But it's really just a notation for giving things a name. Okay? It's a name for that big idea of distribution. It's not a calculation you have to do, it's just a name. Right, so that's all the things that are about giving names that I've thought of at the moment. If you can think of any, please mention them later. Those things are just giving things names. Okay? The next notations are for making statements. So, you may have names for things, like x, and you might want to say something about x. You might want to say that x is equal to 5. That's a statement, it's a sentence. It involves a verb, which is equal to, and it involves a subject and an object. And we're going to find out how that works in maths. But I should warn you that most notations for making statements are read aloud differently depending on context. This thing that is written here is read aloud as, let x be equal to 6. Then x is equal to 1 plus 5, which is equal to 1 plus 2 plus 3. That's how you read that aloud. Okay? Everything that's written there can be read aloud in a grammatical English sentence, or whatever language it is that you're writing in, but with the then and the letter in English. That equals there was read aloud as be equal to. This equals there was read aloud as is equal to. And this equals here was read aloud as which is equal to. So I just want to point it out that the equal sign is read aloud differently depending on context. It means the same thing, but you have to read it differently so that it fits grammatically into your sentence. Okay? So that means that if you want to make any statement like which is equal to, you just need an equal sign, you don't need the word which, because it's part of the equal sign already. So these are all things, statements you can make about numbers. These are the inequality signs, they're called. And they are less than or equal to, and just less than, and greater than or equal to, or just greater than. But again, depending on context, you can read them aloud differently. You can read them as which is greater than or equal to, if you like. And if you have trouble remembering which is which, the small end points to the small number, and the big end points to the big number. Or, as my Year 8 teacher told me, it's a crocodile, and it eats the big one because it's greedy. Right? That helps. Go for it. Maybe not admit it to too many people, but it's fine to think that, right? I won't make you embarrassed if you admit that, but either the pointy end is the small end that points to the small number. Okay? There is equal to, and if you put a cross through it, it means is not equal to. Okay, and that's in general true for pretty much all notations in maths. If you put a cross through it, it means not. So I could go back here and put a cross through the less than, and it would mean is not less than. But that's the same as greater than or equal to, so you don't usually do that. But it is possible to make that statement in maths if you want to. These are three alternative ways of writing is approximately equal to, depending on where you're from. It might be a squiggly equals, it might be an equals with a dot on the top and the bottom, or it might be an equals with only one squiggly line. Depending on what your lecturer does, they all mean approximately equal to. This symbol, that looks like an infinity sign with the end cut off, means is proportional to, and that's used in physics. So that means that they grow at the same rate, but not the same rate, but at the same time, but they're not necessarily equal. Okay, so it usually means that one thing is like 5 times another thing. And that one with the 3 equals, the 3 lines, means is equivalent to. It may mean in some context is congruent to, it may mean in some context is exactly equal to. Depending on context, it means something different, but in general you can read it aloud as is equivalent to. It means I can consider it the same, but it might not actually be the same. So you might have seen that possibly, I saw it at school when we were doing triangles. You say that 2 triangles are congruent. They're not really the same because they're in different places, but I can consider them to be the same. So means is equivalent to. And there are plenty of others that you can think of. These ones are statements that you make about sets. Those previous ones are used for numbers. Okay, 5 is less than 3. X is greater than 17. These statements are about sets. So a set is a collection of numbers or objects. And these statements are concerning whether some sets are contained in other sets or whether objects are contained in sets. So these two are designed to connect 2 sets together. So the on the side U means is contained in, or possibly is a subset of, but you can think of it as is contained in. And you can also do is contained in or equal to, and that's for sets. So you can say, for example, that the set of natural numbers is contained in the set of real numbers. Okay, the set of natural numbers is a whole collection of numbers that go together, and as a collection they're in the set of real numbers. This notation is used for an object and a set. Okay, so this one here, it looks like an E, is read aloud as is in, or more formally is an element of, or is a member of. And you can put a cross through it as well to mean is not in. Okay? And that is specifically reserved for objects being in sets. You can't use that. You couldn't use this symbol here because this symbol is used for objects and that is a set. So since they're 2 sets, I have to use this symbol. For example, the number E is not in the set of rational numbers. That's how you would read that aloud. Okay. But just be aware, you could also read it as which is in, depending on context. And these are statements about other things that probably won't come up very often, but that symbol there means is perpendicular to, and 2 double up and down lines means is parallel to. They'd be used for lines. That symbol there is used for a random variable, and it means has the whatever distribution. So you can say X has the chi-squared distribution with 5 degrees of freedom. You could also read it loud as is distributed according to. Okay? And this is an abstract symbol that you probably won't see, but it's for abstract algebraic objects. It means is isomorphic to, which is the same as congruent, but for sets. So there are plenty of others, and if you see them, please ask. And that's it for things for making statements. Now, combining things for making names and things for making statements, sometimes you can have notation that creates new objects from old objects. Okay? So we have binary operations, which I'll get to, symbols that work on a number, functions, and other complicated stuff. So, operations on numbers. Hopefully you know what these are. Plus and minus and times are fairly self-explanatory. Mathematicians will often use a dot to mean times. Don't get it confused with the decimal place. The decimal place will be on the bottom of the line and the dot will be in the middle. That means times. If they're just using letters, they won't put a symbol there at all. That still means times, but you can read it aloud as just XY. Divided by, there's a symbol for it. If you're in Germany, you wouldn't put the bar through it, it would just be a colon. And 5 divided by 4 is most often written as a fraction as well by mathematicians because they like fractions. This is read aloud as 5 to the power of 4. And it means 5 times 5 times 5 times 5. These are read aloud, that's read aloud as 5 squared, but you can still say it as 5 to the power of 2 if you want. And that's 5 cubed, but you can also read it as 5 to the power of 3 if you want to. Now, an interlude, just in case, there is an order in which you're supposed to do all those operations. Anything in brackets has to come first. Technically, these are braces, that's what they're called. After that, you have to do powers. After that, division and multiplication in the order they're presented. And after that, addition and subtraction in the order they're presented. Most people would know this as BODMAS or BEDMAS. That's what their teacher would have called it. So as an example, this complicated expression here has to be done in a certain order because internationally we make this decision so that everyone knows what's going on. So the innermost bracket is that bracket there, and so that's the one I will have to do first. And then after I've done that, I can deal with the next set of brackets. The top and bottom of a fraction counts as a bracket as well. That fraction bar groups everything on top of it together. And then I'll do the divides and the times, and that's the actual working. So first I'll figure out that, and it comes out to 6. Then I'll figure out each of those things. I'll do that one first because it's the most complicated. So within that, the times has to go first, and it's 24. And then I can figure out what each of those are. That one's 11, that one's 18, that one's 6, that one's 27. And now that I've got that, the division, I'll do the division and the multiplication in the order they're presented. So the 3 divided by 6 is a half. And then I can do the multiplications. So that one's 44 and 3.5. And then after that, I'll do the addition and subtraction in the order they're presented as well. There are even more rules for how you can rearrange things that have minuses and pluses in them, and hopefully you will have learnt them if you need them already. If you've never learned them, you hopefully don't need them, and if you want to know them, just ask me. Come to the Maths Learning Centre and we can help you out with that. Okay, now you don't just have these operations for numbers. You've got plus and minus and times and divide for numbers. You can actually do operations on sets too. So that symbol there is read aloud as the intersection. So that would be A intersection B, or the intersection of A and B. And that symbol is saying we take A and B and we create from them a new set. And its name is A intersection B. Okay, so it's the set of all things that are in both A and B. So the bit that they share. Okay? Right, and I think of it as a cookie cutter. You know, when you're making scones and you use a glass to cut the scones out? Well, we've turned the glass upside down and we've cut the middle out of the A and the B. That's what I think of it as. The big U is the union. So A union B is a set of all the things in either one or the other, or possibly both. And so what we've really done in terms of the pictures, we've just glued those two sets together in terms of our picture. A is this oval and B is this oval, and we've just glued them together to make one big set. So in a way, this is sort of addition for sets. We just lump them into one big set. And then there's also this symbol, which is a backslash. A forward slash is division. And that's read aloud as A without B, or possibly the exclusion of B from A. And so that would be everything that's in A except the bits that are in B. So what I've done is I've taken A and I've taken off the bit of A that was in B. That's the without symbol. So I said before to the person who asked, that's the irrational numbers, the real numbers without the rational numbers. So, cool, I've said it now. But those symbols are specifically reserved for sets. You can't use them for anything else. We can also create new numbers from old numbers by just using a single number. We don't have to join two of them together. Plus joins two numbers together to make a new one. So we can do the square root. We can do the cubed root. So the square root of 25 would of course be 5, but the cube root of 25 would be a ridiculous decimal because there isn't a nice happy number that cubes to give 25. And there's the fourth root, so you would have to square root it and square root again. So if you have a little number in here, it's once you go past 3, it's the whatever root, so the 4th root or the 6th root or the 12th root. Those two vertical lines is read aloud as the absolute value of, or possibly mod, or the modulus of, depending on who is talking about it. And that means that if x was negative, you turn it into a positive number. So the absolute value of minus 3 would become plus 3, but if I did the absolute value of 3, it would still be 3. Okay? So it doesn't mean you can only put positive numbers into it, it means it only spits positive numbers out. And this symbol, the exclamation mark, is called factorial. That's read aloud as 5 factorial, which means you multiply all the numbers up to there. So 5 factorial is 1 times 2 times 3 times 4 times 5. And 7 factorial is 1 times 2 times 3 times 4 times 5 times 6 times 7. And 1 factorial is just 1, because there's nothing to multiply it by. So if you ever see that symbol, that's what it means. Right, and after our creating, you're not going to have 15 minutes left. After my creating, we can do functions as well. So a function is something that you do to a number and it produces an answer. It doesn't have to be done to a number, it can do to something else as well, but normally numbers. So if you see f and then brackets f, it's read aloud as f of x. Okay, it's not f times x, it's f acted upon x to produce some answer. Okay, it's not multiplication. So these are called the trigonometric functions, sin x, cos x and tan x. In general they won't use brackets. And it's not sine times x, it's sine of x, because it's not multiplication, it's much more complicated than that. This symbol is read aloud as ln, at least here in Adelaide. If you read it as ln or lon, everyone will get annoyed, so call it ln. You can call it the natural log if you prefer. And if you do e to that, you'll get x back again. And some people just write it as log. And some computer programs just write it as log. Okay? I did that. This is log base 10 of x, and which is what you use in pH for chemistry. So this is, if you do 10 to the power of whatever that is, it'll give you x. And some people write that as just log x. So you'll notice that log x, depending on context, could mean ln or could be log 10. Ask someone to know which one it is. Generally in science it's log 10 and in maths it's ln. We can create sets as well. This is the set of x's which are in the real numbers such that x is greater than 1. So note that this vertical line here is read as such that. Some people write it as a colon, like, you know, the 2 dots. So the curly braces are telling you that you should start with the set of, and x's which are in are, and x is greater than 1. So this one's read as a which, and this one's just straight. So that's all the numbers that are greater than 1. And what we've given here is a rule for telling whether something's in the set or not. The number 5 is in that set because it's greater than 1. The number 0 is not in that set because it's less than 1. This one is the set of numbers a squared plus 1 such that a is in the real numbers. So this is different. It's not telling me a rule for how to tell whether I'm in or out. It's telling me how to make something that's in this set. So I could pick any a and then I could make something that's in the set. If I pick a equals 1, I'll go a squared plus 1 and the answer will be 2. If I pick a equals 5, I'll get 5 squared plus 1, the answer will be 26. It tells me how to make new numbers, but it doesn't tell me the rule for telling if I'm in there. So the number 0, is that in the set? Well, you have to see if you can write it as a squared plus 1 for something. And the answer is no, you can't. And finally, you could just list the things that are in the set with commas between them. This is the set which contains the numbers 1, 3, pi, and root 2. Okay, so these are how to make sets. If you have a course that involves making sets, please come and talk to us and we'll talk to you more about it. And there's also intervals. Normally you might see this as a point, you know, x is 1, y is 5, but in the context of sets, this is the set of numbers between 1, not including 1, and 5, not including 5. But if I wanted to include 5, I'd use a square bracket. If I wanted to include both of them, I'd use a square bracket. And if I wanted everything above 1, I'd put infinity at the end there. And you're not allowed to put a square bracket next to infinity because it doesn't actually include infinity, because that's not actually a number. And you can read this aloud as, the set of numbers from 5 down. And these are more complicated stuff. This is read aloud as the integral from 0 to 5 of x squared plus 3x dx. This is read aloud as the sum of I squared plus 2 as I ranges from 1 to 7. If you need to use that, someone will explain to you what it means. And if that's confusing to you, you can come and visit the Maths Learning Centre and we'll help you out. This means dy on dx evaluated when x is equal to 3. So if you see a big bracket, like just line like that, it might have a top on it as well. With thing down there, it tells you what to sub into the formula. And this means the limit as x approaches infinity of 1 over x. I should note that while these all look complicated, the answer to all of them is a number. This answer is a number, this answer is a number, this answer is a number, this answer is a number. So that means that if we do other maths with it, we can times them by 5 or add 4 or divide by 7, and we can make new things from these because they're just numbers. And lastly, in the last 1 minute, we can abbreviate things. We can have shortcuts because mathematicians are lazy, they've got enough work to do, and they like to write things with symbols. So that a cross arrow means something different depending on context. X arrow 3 is read aloud as x approaches 3. You saw it in the limit. If you see f colon r goes to r, that means the function f sends the real numbers to the real numbers. It takes real numbers in and it spits real numbers out. A double arrow like that implies that. A double arrow in both directions means if and only if, and it can also be written as IFF. And if and only if means that if one of them's true, the other one's true, or if the other one's true, this one's true. They both mean the same thing. WRT means with respect to for most lecturers, and ST means such that. Your lecturer will use a whole lot of other abbreviations. They might, for continuous, they might write CTS, for example. Just listen to what they say as they write those things, because they'll basically abbreviate things by just removing all of the vowels. And those symbols, the upside down A means for all or for every, and you just read it aloud like that in the sentence. But the backwards E means there exists, and the backwards E with an exclamation mark means there exists a unique, or there exists exactly one. It's really bad form to use these in assignments. Everyone will hate you if you do this. Just use words. Lecturers will use it because they're proud of being confusing, but it's much easier to just use words rather than to use those symbols. These symbols are usually reserved for formal mathematical logic, where you actually do calculations on these symbols. You can use them, but sparingly. All right. So it looks like they're a bit antsy, and I should let them in. I'll take any questions or requests at this time before I turn off the mic. Yep. Yes, this video will go on the website afterwards, and the PowerPoint slides. Yep.
Thank you.
Cool. Thank you very much. Next week's is about how to do a maths assignment. If you're doing a course that's mathematical and you have to do assignments, that's what next week's is about. So feel free to come along. If you didn't sign the roll for the good people at the Transition and Advisory Service, could you come down and do that too, please? And thank you very much. Yes? Oh, our website. So you'll go to Maths Learning and you'll see it says seminars and workshops, and it will have a list. The link isn't active yet because I haven't put it up yet.
All these are all over there.
Yeah.
Yeah.